Hi everyone, this is Isha. I'm one of your 213 TAs, and this is going to be a finals review. I'm going to timestamp in the description of the video what sections are at what times. So if there's a specific thing you're trying to find, you can skip to it. What I'm going to do is a review over what the final format is going to be, and then I'm going to go back over the material that we had in midterm 1 and midterm 2. So if you want to skip that and just go to the section where I start going over the material that we've covered since midterm 2, you can skip to that in the description. I'll put the timestamp below. And then I'll do some example problems from the section of material that we've covered since midterm 2. If you want more review on stuff that we did in midterm 1 and 2, those review materials are posted, and I'll make sure to link them in the announcement that I give so that everyone can find all the files. Okay, so what to expect on the final. This is my best guess. TAs don't have access to the final, so I really can't tell you for sure what's going to be on it. But based on what the announcements have said and the material that we've covered, this is my best guess of what to expect. You're going to have 3 free response questions. It's going to be 1 on axial, 1 on bending, and 1 on torsion. Excuse me. And under the umbrella of axial, what you can expect is normal stress, normal strain. So those are the symbols associated with that. Possibly something to do with Hooke's law, which is involving E and Young's modulus. So you might have like a stress strain curve that you have to find the Young's modulus off of the slope. We also have elastic deformation under an axial load. So that's when you're like pulling a bar and when it's getting longer. You might also have thermal expansion, which is the expansion of a bar under thermal load. So if it gets hotter, it expands. If it gets colder, it contracts. I'm guessing it's going to be some combination of those concepts. For bending, you should expect probably some kind of shear moment diagram. I would definitely recommend knowing how to use the graphical method for this, just because it's so much faster. You might also have to find the centroid or the moment of inertia. For a given beam cross section, and these are in slightly the wrong place. Let's do that. So you're given in the final formula sheet the moment of inertia for a rectangle and a circle, but you might have to derive something for like an I-beam. You should also know the flexure formula, which is stress due to bending moment. Sigma is equal to my over I. And then the last thing you might have to do is beam deflection under bending. So that would be involving the bending tables that we did in the back at the end of the semester, using superposition or using method of integration. Okay, the last free response question is torsion. So that's shear stress due to torsion, tau. You might have to use the polar moment of inertia. You don't have to worry about torsion for anything other than a round shaft, but you should know that the polar moment of inertia is different for a solid shaft and a hollow shaft. You might also have to use angle of twist. Phi is TL over JG. And remember, we use that for a method of superposition when, say, for example, you're fixed on both ends. You have to determine the angle of twist at a certain point. And you should also know, just generally, how to deal with the factor of safety and with statically indeterminate problems. Basically, all you really need to know with factor of safety is that it's the ratio of what you get over what you want or what you're allowed to have. And so your factor of safety always wants to be at least 1, and based on the wording of the question, it will probably tell you how to set up that relationship. As far as logistics, your final's on Wednesday, May 6th, starts at 2:30. The problems are going to be available on Canvas for 105 minutes, so that would be until 4:15. There isn't anything to submit on Canvas this time, you just look at the problems on Canvas. And then after Canvas closes, you have an additional 15 minutes to take pictures and submit all of your work and answers on Gradescope, so that will be open until 4:30. If you have technical difficulties, email your instructor before the Gradescope deadline closes. And there's also a new rule that your ASU ID should be included in your submission somewhere. So I know the professors have explained this slightly differently to different classes, but something that I think some professors have said, like, take a selfie with yourself and your ASU ID, and a picture of your work, and then just scan the rest of your work. So just based on what your professor explained to you, just stick with that. If you don't have your ASU ID for some reason, use a different photo ID and also email your instructor letting them know to expect that you didn't have your ASU ID so they can like do some additional verification if they have to. The exam is open note and open book, so if you don't have the book, I've screenshotted the beam deflection tables and also the I-beam tables from the back of the book so you can reference them. I'll attach them in the PDF of the notes that I post onto Canvas. Please don't redistribute that information. I think it's copyrighted or something. Last big rule, you have to be in the Zoom meeting during the exam. This is something I think they decided pretty recently, so you might not have heard it in lecture. So make sure you're in the Zoom meeting during the exam. If you have any questions, don't say them over the microphone. Put them in chat so you'll be able to directly ask the instructor. Last but not least is manage your time. It's like we've experienced in midterms in the past. Tests are always kind of time limited, particularly because they'll probably have multiple parts. So if you're feeling like you're getting really bogged down on a problem, I would say go ahead and skip that one. Try to work through everything that you know and then go back to whatever you don't know at the very end. If you feel like you're really stuck not being able to find a certain value, I would write a note that says, I'm not sure if this is the right value, but I'm going to assume that m is equal to 100, and then do the rest of your calculations based on that assumed value, just so you can prove that you know how to do the process. There will be partial credit like given on the final, so you want to show as much work as you can. You want to show all the equations that you're using. Okay. So I am going to go quickly over the material from midterms 1 and 2. If you want to skip this, you're welcome to skip this. There's a review of fundamentals, so like really basics. Supports have two support reactions, a reaction in the x direction and a reaction in the y direction. A roller support has just one reaction in the y direction. If you have a fixed end, you have 3 reactions, an x and a y, and also an a moment. And then lastly, if you have something like a rope, you're going to have just the one force in the direction of the rope, in the direction the rope is facing. If you have a truss, that is a bunch of pinned joints where forces act only at the joints, you can use either the method of joints or the method of sections. If you're using method of joints, you're going to look at a specific point, take the sum of forces in both directions, and then move through the structure in order to find all the forces. If you're using method of sections, you're going to take a cut across the entire structure, and then take your sum of forces and then also your sum of moments, and that will help you solve for your unknowns. You can also combine them. You can use method of sections and method of joints in combination. Just depends on what the truss looks like and how you need to solve it. Okay, for distributed loads, a rectangular distributed load, you take the area under the W, and that will give you the force. So for example, for rectangle, W times L, and that acts at halfway in the middle of the beam. For a triangle, it's 1/2 W times L, and it acts at 1/3 of the beam. Units. For stress, your units are for force over area. So that applies for normal stress as well as shear stress. For metric, that's going to be units like Pascal or kilopascal or megapascal, which is newtons per meter squared. For imperial, it's going to be pounds per inches squared, or PSI. Something really important is if you have a problem that gives you feet, make sure you're converting into inches before you use PSI. So yeah, remember to convert all of your variables, all of your units to base units. Last thing is taking sections or cuts. So if you're taking a cut of a static member, you're going to have internal reaction forces. So if you have a bunch of different external forces on a beam, you're going to make a cut between each external force. So try to be consistent with which side you keep and which side you throw away. You are allowed to mix it up, but sometimes it can get confusing with what's positive and what's negative. So personally, I prefer to try to keep everything like consistent. So like always throw away the right side or always throw away the left side. Remember that some internal forces might equal 0. So here you've got a cut. You always have a normal away from the cut. You have a shear, which is parallel to the cut, and then you have a moment. So take this like brief example. If you have these two forces acting on a cantilevered beam, you're going to remove the support and add the support reactions, indicate where you're going to cut, and then take one at a time, and always keep just one side. When you take the cut, always add your internal forces and try to throw away any unknown support reactions. So for example, I have a fixed support here, that's 3 unknowns. But if I'm taking a cut in the middle of the beam, I can actually just throw away the entire left side of the beam, and then I don't even need to worry about the support reactions at my fixed end. Okay, that's the material we did on midterm 1. For midterm 2, we had torsion. Like I said before, in this class we only deal with torsion of a circular shaft. So a couple variables you need to know is that torque, which is represented by T, is a moment that twists a shaft. That's going to be units of Newton meters or pound force inches. You have an angle of twist, phi, which is a measure of how much twist is caused by the torque. That's in terms of radians or degrees. You've got torsional shear stress, tau, which is the stress caused by the moment that is twisting the shaft. That's in pascals or psi. And then you have the polar moment of inertia, which is J, which is a measure of how much the shaft resists twisting. And the units for that are meters to the fourth, inches to the fourth, etc. The only two polar moment of inertia equations you need to know are for a solid shaft and for a hollow shaft. And you've got this torsion formula, which gives you stress based on the torque and the radius from the center of your shaft to the outside of your shaft, and then J, which is your polar moment of inertia. You might also see this equation as T rho over J or Tc over J. These are all just different variables that mean R radius. C in particular is used for tau max, where C is the distance from the center of the shaft to the outside of the shaft, because your shear stress is always biggest at the outside of the shaft because that's the part that's getting twisted the most. You've got your angle of twist formula. Phi is TL over JG. We talked about everything except for G, which is the shear modulus. This is a material property. It's generally a pretty big value, so don't worry if it's really big. And this equation gives you angle of twist in radians. So if you're looking for degrees, make sure you convert to degrees. Statically indeterminate problems for torsion generally look like two things. Either you're fixed on both ends and you're twisting in the middle, in which case you know your angle of twist between A and C has to equal 0. And then you rewrite angle of twist from A to C in subparts. So from A to B plus from B to C has to equal 0. The other type is if you have like a composite material, so for example aluminum on the outside and steel on the inside, and the whole thing is being twisted, in which case you know the angle of twist of each material is equal to the other. Okay, so we have bending, which is the other big topic we covered in midterm 2. So the first thing we did with bending was shear moment diagrams. The process you're going to do with those is always first find your support reactions. Second, you can use method of sections or the graphical method in order to actually draw your shear moment diagrams. And then you use that to find values like, for example, maximum moment or maximum shear stress. For the graphical method, remember that your magnitude of your distributed load is equal to the slope of shear, and your shear is the magnitude of your shear is equal to the slope of moment. So that means also, in order to find the change in your shear for your diagram, you can take the area under your distributed load, and to find the change in moment, you can take the area under your shear diagram. Also really important, sign conventions for graphical method are a little bit confusing. The first two make sense. If your distributed load is pointing up, it's positive. If it's pointing down, it's negative. For point forces for your shear, if a force is pointing up, it's positive. But for moments, point moments, so like external moments that are acting on your beam, clockwise is actually positive, not counterclockwise. I know this is confusing. It's basically because this is the standard that will help our graphical method match the results from our method of sections. Or like from like your integration or whatever it is that you're doing. The way that I like to remember this is the reason that clockwise is positive is because you have an external moment and your graphical method is graphing the internal reaction. So if you have an external moment which is clockwise, your internal reaction is going to be counterclockwise, and we know that generally using right-hand rule, counterclockwise is positive. So if you think of external moments as being external, then it makes sense that the moment is going to be like opposite from what we're used to. So yeah, just keep in mind if you're using graphical method, an external moment is positive if it's clockwise. Okay, bending stress is the other big thing that we need to calculate. A couple variables are bending moment, which is M is the moment that's bending the beam. Your neutral axis is the axis where stress and strain are both 0. If you have something that's symmetrical, it's always going to be down the middle, so like a rectangle, down the middle of the rectangle, or a circle. Otherwise, you locate the neutral axis using the geometric centroid. That's the centroid of a compound is equal to the sum of the centroids of each subcomponent times the area of the subcomponent divided by the sum of all those areas. And there's an example of this in the midterm 2 review if you want to go back and look at it. Your distance y is your perpendicular distance from the neutral axis to the point that you're evaluating. Basically, as you get further and further away from the neutral axis, which is 0, your stress is going to get greater and greater. Lastly, we have moment of inertia, which is I, which is how much the beam resists bending. It's very similar to the polar moment of inertia, just calculated differently. And you're given the moment of inertia for a rectangle and a circle, and you can use these to derive, for example, if you have an I-beam, you can use the moment of inertia of a rectangle to derive the compound moment of inertia for an I-beam or an L-beam or something like that. And you do that by taking the sum of all of the subcomponent moments of inertia plus the area of each subcomponent times the distance squared from the neutral axis of the entire cross-section to the neutral axis of the subcomponent. There's also an example of this in the midterm 2 review video. Lastly is our bending stress formula. That's going to be sigma is equal to my over I. M is the moment, y is your perpendicular distance, and I is your moment of inertia. The reason there's a negative here, actually, honestly, I don't really know why there's a negative other than just like it helps us keep with our sign conventions. But you will want to know that for bending stress, if you're plugging in M max, you're going to plug in the absolute value, generally based on the way the problem is phrased. And that tension is going to be positive and compression is going to be negative. So that's midterm 2. So let's go over the material that we've done since midterm 2. So I want to go back and revisit a couple things, just because I think they're a little bit confusing still. The first thing is shear moment diagrams. You always go from forces on the beam into your shear diagram and then to your moment diagram. So basically you increase one order each time. So if you start with a point load, your shear is going to look like a rectangle and your moment is going to look like a triangle. If you start with a rectangular distributed load, your shear is a triangle and your moment is a quadratic. And if you start with a triangular distributed load, your shear is a quadratic and your moment is a cubic. For your shear diagram, know that point loads cause jumps. So a positive point load, jump like a point load pointing up, is going to cause an upward jump in your shear diagram. And that the area under the distributed load on the beam gives you the change in shear. For a moment, again, external moments cause jumps. Remember that clockwise is positive, so clockwise causes a jump up in your moment diagram, and that the area under your shear gives you the change in moment. I also wanted to revisit bending stress really quickly. Remember that bending stress is always 0 at your neutral axis. And if you have a moment, so in this example, our moment is acting like this way, you're going to see that it's causing positive in one direction for half of the beam and negative for the other half of the beam. We know that tension is positive and compression is negative. So in this case, we're causing tension on the bottom of the beam and compression on the top part of the beam. And you see that it's 0 at the neutral axis and it increases as you move away from the neutral axis. So your maximum bending stress is going to be at the point which is the furthest away from your neutral axis. Okay, so new material. The first thing that we did was something called prismatic beam design. It's based off of this equation. S required is M max over sigma allow. So basically you have your maximum moment, which is something that you take from your shear moment diagram, and then you have an allowable stress. So that's usually a material property. So like steel can be allowed to have a certain amount of stress on it. You can use your appendix A to select an S, which is bigger than your S required. And so for example, something might look like W 18 times 46. The first number is the depth of your beam cross-section. So if it's an I-beam, it's going to give you the depth of the I-beam. And then the second number is the weight. So if you have a problem that tells you to minimize weight, you'll find an S value, which gives you a pretty small weight while also being greater than your S required. And your units for S is inches cubed, meters cubed, etc. Okay, so for beam deflection, I wanted to establish a couple things. First of all, we have a couple sign conventions. So the way I like to remember this is that your positive moments are going to make the beam smile, and your negative moments are going to make the beam frown. So your positive moments, depending on whether you're looking at the left side of, like the left end of the beam or the right end of the beam, are going to be clockwise and counterclockwise. Those are positive because they're making the beam bend up. The other ones are negative because they're making the beam bend down. The other thing we have is a positive sign convention for when you make cuts. So if you're cutting on the right side, your shear is going to point down and your moment is going to be counterclockwise. If you're cutting and then like taking the right side, getting rid of the left, your shear points up, your moment also like curves up, but that's clockwise. Okay, so for boundary conditions, basically for beam deflection, the first thing you're going to do is just like look at the beam, what forces are acting on it, and kind of try to guess what it looks like the beam, like how it looks like the beam will change. For pins and rollers, your boundary condition for beam deflection is that you can't deflect at a pin or a roller. So the beam has to be in contact with the pin or roller at that point. So here you have a pin. You can see that the purple line, which is the deflection line, is touching the pin. And then you have a force that points down. So that's making it bend downwards. But then we know that at the roller, it has to be touching again. So it bends down and then it bends back up. And then we have another force which causes it to bend back down. At fixed supports, you have the no deflection rule, which is the same as pins and rollers. You have an additional boundary condition, which is that you can't have a slope at your fixed support. So what that means is here, not only is it touching the fixed support here, it's actually going to continue, and the slope leaving the fixed support is not going to bend. It will eventually bend, but right coming out of the fixed support, it will have no slope for a little bit. Basically, you're drawing deflections to get an idea of the shape. It doesn't need to be perfect, but it will help you as you reference it for the rest of your problems. Okay, so for our elastic curve, we basically use a process of integration. We have our distributed load is equal to EI, and then the fourth derivative of your deflection. Your shear stress is the third derivative of deflection, and your moment is the second derivative. And then we use this basically to integrate to find the slope and the deflection. For the elastic curve, E and I are both like kind of properties. So E is a Young's modulus. That's a material property. So if your whole beam is the same material, E is constant. I is the moment of inertia, which is based on the beam cross section. So if your beam is all one uniform cross section, your I is also constant. This is helpful because sometimes we encounter situations where we can actually count, cross out E and I, like we can cancel them out because they are constants. And then you can deal with beam deflection in two different ways, the method of integration and the method of superposition. The method of integration is basically you find an equation which represents m in terms of x. So how does the moment change in terms of x? You integrate it once to find the slope, and then you integrate it again to find the deflection. After that, you use boundary conditions to solve for C1 and C2, and then you can back solve to find all of your unknowns, whatever you're looking for in the problem. For the method of superposition, you're going to break down your multiple loads into individual load cases. Use the tables from Appendix A for cantilevered or simply supported beams, and you're basically going to add them all up in order to find deflection or angle or whatever it is that you're looking for. For statically indeterminate problems, for beam deflection, basically what you're going to do is compare the number of support reactions you have to the number of equilibrium equations you have. And if you have too many support reactions, you know that it's statically indeterminate. Basically, what you do in this case is you select and remove a redundant support in order to find what's called the primary beam. It doesn't really matter which supports you remove. You just want to remove whatever is easiest for you to do the actual calculation. And then you add just the redundant one at a time and then write a compatibility equation based on that. So an example is kind of the easiest way to describe this. So in this case, we have 4 support reactions and only 2 equilibrium equations. We can't really take the sum of forces in the x direction, which means we have 2 redundants. So first we're going to find the primary beam. In this case, we've left supports A and D just because the table, which we use for method of superposition, will give us equations based on having 2 supports, one on each end. So that's the easiest thing to have as our primary beam. So for the primary beam, you remove your redundant supports, but you leave all of your external forces. So P1 and P2, we leave those. We draw the elastic curve, and we have a deflection at B and a deflection at C. Next, we're going to add each of the redundant supports only one at a time and remove all of the external forces, the applied forces. So based on just your reaction at B, you have a deflection at B and a deflection at C. Based just on your reaction at C, you have a deflection at B and a deflection at C. And then we can write compatibility equations based on this. So for example, at roller B, we know that in reality, the beam has to be touching B because it's a roller, it's a support. So that means we know that our overall deflection is equal to 0. And so that means we take VB here plus this value plus this value. So we add together all of the different deflections, and we know that that equals 0. And we do the same thing for C, and then we can solve for our reactions at B, our reaction at C, and then use those values to solve for our reactions at A and D. This will make more sense with an example, I promise. Okay, so that's our overview. I'm going to kind of talk you through a couple practice problems. I'm not going to write as I go, just because it takes forever and it's not neat. So I'm going to talk you through these problems that I've already solved, but if you feel like it's going too quickly, you can always pause the video and look at the work. I've also posted a PDF of the work on the Canvas, so you can always go back and reference that as well. Okay, so this is a problem out of Chapter 11, which is a prismatic beam design problem. And for our purposes, we only care about bending stress. You're going to learn about shear stress in this context in 322, which is the next class. So for this problem, we're just going to focus on bending stress. So the problem wants us to select the lightest weight wide flange beam from Appendix B that will safely support the loading shown. The allowable bending stress is sigma allow is 24 KSI. Okay, so the first thing you always do is find your support reactions. So I've drawn my support reactions for a roller here and a pin at B. I've taken my sum of forces, my sum of moments, and my other sum of forces, and that helps me find AY and BY. After that, I am going to go ahead and do my shear moment diagram, because in order to find S, I need to know my M max, and the only way to know my M max is by doing a shear moment diagram. So I've redrawn the beam here with all of the forces that I now know, and I've gone ahead and done a shear moment diagram. So here we have an external point force. We know that point forces cause a jump in our shear diagram. In this case, the point force is pointing down, so it causes a negative jump down to 15. Between this point and where the distributed load happens, nothing is going on the beam, so it's just going to be a straight line across. We are at negative 15, we're just going to continue to be at negative 15 until something happens, which is that AY is another external point load, which is pointing up, so it's going to cause a positive jump. So from negative 15, we have a positive jump of 40 up to 25. And then from there, we have this triangular load, which, if you remember, you're increasing your order each time. So the triangle is order 1. It's like a line. You're going to increase the order to an order 2, which is a quadratic. Our distributed load is pointing down, which means it's going to be it's going to be a decreasing quadratic. So we go from 25 down all the way to 2.5, and we know that BY, which is a point force, which is actually pointing down. So when you solve for the reaction supports, it becomes a negative value. So when I drew it here, I drew it downwards, being equal to 2.5. Anyways, so that causes our very last negative jump back to 0. So always remember that your shear diagram and your moment diagram start at 0 and end at 0. So that's a good way to check that your diagram is looking correct. From here, we're going to drive our moment diagram. Once again, we start at 0. External point loads don't affect your moment diagram. If there were an external moment, so for example, if there was a moment here, that would affect my moment diagram, but there's not, so we don't worry about it. Oops. Okay. So nothing happens in terms of moments until we get, nothing happens in terms of moments at the beginning. So we have this shear diagram, and we know that the area under the shear diagram gives us the change in M. So in this case, it's negative, it's under the x-axis, so we know that it's decreasing, and it's decreasing at a slope of negative 15. So if we decrease at a slope of negative 15 over the course of 6 feet, we end up with negative 90, which is the area under the rectangle here. We know this is a quadratic, so there's going to be a cubic, and we know we have to increase back to 0. So it's going to be a curved increase back to 0. Because our shear is positive here, it's above the x-axis, it's going to be a positive increasing, and we go from negative 90 to 0. So based off of this shear moment diagram, basically from the moment diagram, we can tell that M max is going to be a value of negative 90 kip feet. So this is what's really important, what we're getting out of the shear moment diagram. We're going to take that into step 3, which is beam design. This equation is off of your final equation sheet. S required is absolute value of M max over sigma allow. We found this negative 90 here, and we know from the problem statement that our sigma allow is 24. So I'm going to plug in those two values. I'm also going to convert kip feet into inches because our KSI is in inches. So I'm multiplying by 12 inches over 1 foot. Based on that equation, we get our S required is 45 inches cubed. Now we're going to go to the table and try to identify an S which is bigger than 45, but not by a lot. So we're going to go into this table. What I've boxed here in the XX direction is what we're looking at, our S's. And I'm looking for numbers that are bigger than 45, but not by a lot. So I got these two options. They both fulfill my requirement, but remember that the problem statement said we wanted to choose the lightest weight beam that we could. So if I'm going to take this number, if I trace it back over here in the table, I have W16 by 31 or W14 by 34. We remember that the second number is the weight, so we're going to choose the lighter option. So our answer for this problem is W16 by 31 is the best cross-section to choose for this problem, which will fulfill our requirements while still being the lightest weight wide flange beam we can choose. And this appendix I'm going to post like references at the end of the PDF in case any of you don't have access to your textbooks. Okay. Another beam design problem, slightly different. It doesn't use the table. I'm gonna get some water. Okay. Problem 1122, and these are all out of the 10th edition of the textbook. So, if you have access to it, you can always go back and look at all of the recommended problems that the professors have given you, and you should be able to find these problems. Once again, we're ignoring shear stress, so I've crossed that out of the problem. We have a beam. Having an allowable bending stress of sigma allow is 1.1 KSI. Determine the width B if height is H is equal to 2B. So we have a rectangular cross-section, and I know my moment of inertia equation for a rectangle, so I'm not going to worry about that for now. The first thing I'm going to do is find my support reactions, once again, sum of forces and sum of moments. And once I know my support reactions, I'm going to go ahead and do a shear moment diagram. So I've redrawn the beam here with my known reactions now, and for the shear diagram, once again we have a point load. It's pointing down, so I'm going to have a jump downwards to negative 800. Then nothing happens until my distributed load. Here I have a point load at AY, which is positive 1380. So I go from negative 800 to positive 580, which is a change of 1380. From here, I have a rectangular distributed load, which is pointing down, which means it's negative. That means my slope is going to be negative. It's going to be negative 80 because my distributed load has a magnitude of 80. So from 580, I'm going to have a slope of negative 80 over the course of 6 feet. That will take me from 580 to just 100. At this point, I have another point load. I have BY, which is 140, so it's going to jump me up to 240. And then from 240, I'm going to decrease again at a rate of negative 80 over the course of 3 feet. That takes me back to 0. So this is another good check. I started at 0, I ended at 0. From the shear diagram, I'm going to draw my moment diagram. So we start at 0. Because our shear value is negative 800, my moment is going to be at a slope of negative 800. From 0 over the course of 3 feet, we get to negative 2400, which is 800 times 3. From here, I have a triangle, so I know that this is going to be a quadratic. It's above the x-axis, so it's positive, so I'm going to be increasing. If I take the area under this trapezoid, I know it looks like a triangle, but it actually doesn't touch the x-axis here, so it's a trapezoid. If I take the area under that trapezoid, it tells me the vertical change in my moment. So from negative 2400, if I take the area under the trapezoid and add it to negative 2400, I get negative 360. from negative 360, I will increase to 0, and I can check that again. My displacement from negative 360 to 0 is the area under this triangle. So you can verify that you start at 0, you end at 0, based on the areas under this trapezoid and this triangle. So from my moment diagram, I can tell that M max is negative 2400. I'm going to take that value and plug it into my beam design. So we have this equation once again, which is from your final equation sheet, which is S required is M max over sigma allow, which is equal to moment of inertia over C max. So I know I'm going to need my moment of inertia, so I'm going to just go ahead and do that first. So I have this rectangle. They told me that my width is B and my height is 2B. My neutral axis, because it's a symmetrical rectangle, is going to be just in the middle, and my C is going to be my distance, kind of like how your radius was in other bending problems. Your C is going to be your distance from your neutral axis to the outside. So based on this equation for rectangular moment of inertia, I'm going to plug in my values for B and H and calculate that out, and I get that I is equal to 2/3 B to the 4th. Okay, so I'm going to take that number, I'm going to plug it into this equation. I know my M max, I'm going to take the absolute value of it. Once again, I'm going to convert from feet into inches because my units here were feet. I'm going to convert from feet into inches. I know my sigma allow is 1.1 KSI. I'm going to convert that into PSI. So I'm multiplying by 1,000 here to get 1,100 PSI. So that's my M max over my sigma allow is equal to I over C max. So in this case, my C max is just B. It's 2B divided by 2, which is B. And my I already calculated. So based on those values, I'm going to solve for B and get in the end that B is equal to 3.4 inches. So based on the givens that they gave me and the M max that I found, the base of this Douglas fir beam, which is a rectangle, is going to have to be 3.4 inches in order to have the allowable bending stress that it asked for. Okay, so that's beam design. Relatively straightforward, I think. So we're going to move on to beam deflection. And for beam deflection, there's two methods. There's the method of integration and the method of superposition. So I'm actually going to solve this one problem in terms of both, just to show you how kind of each one plays out. I would really recommend you use method of superposition wherever you can on the exam, just because it's going to be time limited and the method of superposition is much faster. Okay. So problem 12-106 is asking you to determine your support reactions at A and B, given that E and I are constant. So the first thing you do is check your reactions. You have 4 support reactions, 1 at the roller and 3 at your fixed support. That makes 4. You can only get 3 out of your equilibrium equations, which means you have a redundant support, so this problem is statically indeterminate. So we're going to deal with this using the method of integration first. And so what we're going to do, I've just redrawn the beam here with my support reactions. I'm going to use my equilibrium equations to determine, I know that AX is 0, and then I have these 2 equations which have a bunch of unknowns in them, but I'm going to keep them and I'm going to number them because I'll need them later. Okay, so looking at this problem, I know my fixed support presents kind of a problem because it has 3 unknowns. So I'm actually going to, when I make the cut, I'm going to throw away the left side of my beam. I'm going to get rid of this because it's a lot easier to deal with my 1 unknown over here, by, than my 3 unknowns over here. So you can see that I'm starting X from the right side and going towards the left, and I'm going to make a cut just so I can reference it. And that is in order to find my moment function. So the first thing I've done is I've calculated what W will be, right? Because your W naught only applies at this top point of your triangle. So if you cut your triangle, you have to find the new W value. And that's going to be your slope, which is W naught over L, multiplied by X, which is whatever distance you're making the cut at. Based on this, I can take my sum of moments here at the cut. So I get whatever my moment is in terms of X, which is acting on the cut, minus my distributed load, which is calculated here, plus so a negative moment based on my distributed load, and then a positive moment based on my support reaction here. Based on this sum of moments, I'm going to calculate for my moment function m in terms of x. Yeah. So once I have my moment function, I'm going to go ahead and integrate it. So you remember this from the equation sheet is going to be EI the second derivative of deflection is equal to moment in terms of x. So I know my moment in terms of x. I'm going to go ahead and integrate it first. Integrate it once in order to find my my deflection, my change in deflection. Change in deflection is also known as the slope, so this is also your slope equation here. Okay, so I'm going to integrate it once. That gives me integrating it in terms of x gives me this, and then I have to add a plus c1 at the end because there is an unknown there. So this is going to become my equation 3. I'm going to integrate it one more time to find deflection, which is going to give me c1 times x plus c2. These are constants because, once again, you're integrating without bounds. So this is going to become my equation 4. So now we have a bunch of unknowns. We're going to use boundary conditions to calculate c1 and c2. So if you remember a roller support, which is x equals 0 in this case because I put it here. At a roller support, x equals 0 and deflection has to equal 0 because the beam has to be touching the support. So I'm going to plug this into my equation 4 and find that I can cross out a bunch of things that are 0 because of this, and I find that c2 is equal to 0. Next, I'm going to look at my fixed support, which is at x is equal to L, which is the length of the beam. I know that the angle is also equal to 0. So the angle is the change in deflection. So I'm going to plug that into equation 3 in order to find C1. That gives me this value. And then I can plug it in. And then once again, at the fixed support, I know that my deflection is also equal to 0. So I'm going to plug it into equation 4 again. Now that I know C1 and C2, I can plug those in. And that helps me find my support reaction at B. Once I have my support reaction at B, I can go back and plug it into my equilibrium equations to find the other two supports. So I know my By is equal to W naught L over 10. Here, my equilibrium equations 1 and 2, I can plug them in. Ooh. Hello. I can plug them in here to equation 1 and 2 to find my AY and my moment at A. Those are my support reactions that I wanted to find, right? Because I already know that AX is 0. I now have AY, I have my moment at A, and I have my support reaction at B. So this is what the problem was asking for, but it is kind of a long and convoluted process. So I will post this PDF to the Canvas. You can look at it slower if you need to, but I'm just going to go ahead and solve the same problem using the method of superposition because it is significantly easier. So we're going to go back, look at the problem again. We do the same thing. We checked our reactions. We know it's statically indeterminate. What that means in terms of method of superposition is that I have to break it down into parts and have a compatibility equation. So these equilibrium equations are the same as before, but now I've taken my beam and I've broken it down into two sections. First for my distributed load and second for my point load. And I've done this because the tables have like a whole section on cantilevered beams, and there's a case for a triangle distributed load, and there's a case for a point load. So based on these two, I'm going to draw what I think like the change in the deflection will look like. So I have a downward distributed load that's probably going to cause a downward deflection, and upward support at B is going to cause an upward deflection. And so I'm going to try to find my deflection at B for both of these points. I'm using the tables, and for each of these, my deflection is actually deflection max, V max, because like the deflection gets bigger the further you get along the beam, and because B is at the very end of the beam, the deflection is the biggest there. So I've applied my tables. I found that VB is this value here. It's negative because it's a downward deflection, and then this value here, which is positive because it's a positive deflection. So I have VB, I have VB prime. Based on this drawing, I'm going to find a compatibility equation. In this case, I know that at my roller support, my deflection has to equal 0. So that means that my VB plus my VB prime has to equal 0. So I'm going to plug in those numbers, and then I can cancel out EI because they're constants and they're equal to 0. Or like I'm setting the equation equal to 0, so I can cancel them out. And then based on that value, I can find BY, which is W naught L over 10. And if you recall, that answer is the same as the answer we got from the method of integration. From there, we're going to do the same thing we did before, plug into our equilibrium equations to find AY and our moment at A. I think you can generally just kind of see how much simpler it is for this use case to apply the method of superposition. Obviously, the method of superposition does have its limitations. It only applies, like for example, let's take a look. It only applies point loads at L/2. For a simply supported beam, it also has a case for a P acting somewhere along the beam. But for a cantilever, it only has a case where your P is at the very end of the beam or where your P is at the very middle of the beam. So if you have a cantilever and your P is acting, for example, at 1/3, you don't have an equation in the table in order to use that. So it does have its limitations, but where you can, I would try to apply it just because it is much faster. So that's all the problems I have for you guys. I'm going to timestamp each of the problems just so you can skip through them as you need to. And I will also post this reference with the deflections and your wide flange sections in case you are one of those people that, for example, left your textbook at your dorm or something and you don't have access to it. I'm going to post an announcement for this on the Canvas and link the previous video as well as our previous review materials so you can go over those as well in more detail. We've got example problems from midterm 1 and midterm 2. I'll also set it so that you can reply to the announcement. So if you have any questions about this or about like the final in general, you can go ahead and put them there and I will do my best to answer them. That's all I have. It's been a pleasure to TA for you guys for this semester, and good luck on the final.